It's audio working. You got a highlighter, highlight just on this page like this a little bit. All you gotta do is really outline it, but if you're just sitting there doing nothing, you have a highlighter, go to page 17. It's just to distinguish easier the SPDs. It doesn't, you don't have to highlight either. But if you're doing nothing, it might make it easier.
I don't know if you got my email, but today I was clicking the PDF and I actually opened the quiz. I didn't take it, but like, I don't know. I basically like, can I like did it like retook on the 26th instead? The chapter 6 and 7 take on the quiz. I actually opened it.
Why? Because it says do not open unless you plan to complete this quiz in capital letters. Yeah. So why would you open it?
I don't know. I just an accident.
What's that? Were you just clicking at stuff?
Yeah, like I thought it was the PDF. I'm not gonna lie.
You sent me an email?
Mhm.
I think, well, I need to check my email.
Okay.
I'll look at it.
Okay, sounds good. Thank you.
I just made my S's one color, my P's one color, D's one color. Just, it's not a big deal, but just to see it better. All right, so let's see, we just got quiz question number 2. So let's do this. We've got C is equal to lambda F. This is the speed of electromagnetic waves. We know that this is 3 times 10 to the 8 meters per second. This is our frequency. You're going to solve that for your wavelength, and the answer is going to be in meters. Change it to centimeters. This is going to work out to meters after you solve this, and then change it to centimeters. Okay. So let's see where we left off. And I think we left off. We did electron configuration notation and we did the blank periodic table last time. We did a lot. So today we're going to do valence electrons. We're going to do quantum numbers. So we left off. So we did what's called the off-ball principle, which is the order that electrons fill the shells around the nucleus. And if we have 7 shells, then we know that we can put all of our electrons are diagrammed with this, and that's exactly where we left off on the blank table. Wherever I put the blank table, we completed this blank table. Then I said, this is where it doesn't work. There's other places it doesn't work, but we can explain these two later on. Okay, so now what I want to do is I'm going to go back to this page, which is our electron configuration notation. And at the end, I said there is a shorthand way to do this, which is to put the previous noble gas in brackets and then just do what's added to it. So neon's configuration is to here, right? That would be the configuration of neon. If we did iron down here, the next one, my noble gas is to 3p6. And if I go to 3p6, I have the noble gas. Argon, right? Argon ends in 3p6. So this, the shorthand way to do it is we'd have argon in brackets and then 4s2 3d6. Okay. Now, I'm going to complete some more of these just because we need them. And maybe you've got them done. And maybe I can stop there. Now, the next page, the 16 on the next page match up with the 16 here. And on the next page, we're going to do what's called arrow notation. So every electron is going to have an arrow. So I need to back up here to page 13. So on page 13, at the very bottom, in 1921, Otto Stern and Walter Gerlach performed an experiment that probed the magnetic behavior of atoms by passing a beam of silver atoms in the gas phase through a magnetic field. The Stern-Gerlach experiment showed there are two orientations for the atoms, with the electron spin aligned with the field or opposed to the field. That is, the electron spin is quantized. This fact is accounted for by introducing a fourth quantum number, the electron spin quantum number. Now, if this lines up with the field going this way, and this is spinning counterclockwise, this would be counterclockwise. We use an up arrow for the electron spin, and clockwise, a down arrow. Now, think of this as if you're spinning a basketball on your finger. There's only two orientations you can do. You can either spin that basketball clockwise or counterclockwise, correct? And you've seen people do that. Okay, so we are going to signify the spin of the electron with an up arrow or a down arrow. Okay. Now, on this page right here, this 1 through 16 goes with the original 1 through 16. So number 1, my configuration was just 1s1. Each one of these boxes represents an orbital. How many electrons can I put in an orbital? 2, correct? 2. This is all my max would be 1s2, 2s2. How many electrons can I put in the entire p sublevel of 3 orbitals? 6, right? Which would be 2, 2, 2 for 6. And the D's would be 2, 4, 6, 8, 10, correct? 2 electrons max per orbital. Now, I just have 1s1. I'm just going to put an up arrow. Now, if you have 2 electrons in the same orbital, they must be spinning the opposite direction. But for this case, it's hydrogen. I only have 1 electron. It could be spinning the other way. I'm just going to circle it. That means it could be spinning the other way. An up arrow or down arrow, that's all we can do. There's 1 electron. We don't know which way it's spinning. Now, the next element was 1s2, 2s2, 2p2. From the previous page. Right now, these numbers match up here. So we got 1s2, 2s2, 2p2. So if I have 1s2, one's going to be spinning up, the other one's going to be spinning down. There's my 1s2. My 2s2 is the same way. Now, don't get ahead of me. Don't get ahead of me. You'll be frustrated. 2s2. So that's my 1s2, 2s2. I'm left with 2p2. And in order to do 2p2, we have to do Hund's rule. We have to do this according to Hund's rule. Well, Hund's rule says this. We can put it right up here, or we can look back a little bit. But let's just put it right here. I can word it better. You put one electron in each orbital of the same spin. Before pairing. Of the same, I lost the word, I missed the word spin. Oh my God, spin. One electron in each orbital of the same spin before pairing. So that's Hund's rule. One electron in each orbital of the same spin before pairing. Now that means this. If I end in D5, it would look like this. If 1, 2, 3, 4, 5. I have 5 d orbitals, correct? So if my electron configuration notation ends in D5, I have to do this one electron in each orbital of the same spin before pairing up. I'd have to do 5 all up, or five all down, right? One electron in each orbital of the same spin before pairing. That is particularly stable. They like a D5, half filled, 5 up or 5 down. So when I go here to 2p2, it also works with the p's, the same thing. I need to put one electron here, or one here, and one here, or one here, and one here. You don't know which one of these is going to go in. 2 out of the 3. I'm just going to do it left to right, and I'm going to put 2 of them up. This has to be the same. 2 up or 2 down, correct? My electron configuration for the next one ends in 2p5. So if this ends in 2p5, I would have 1s2, 2s2. Now I need 2p5. If I had 2p3, I could do this. And you have to do it this, well, you got to go 3 up or 3 down in the beginning. That's my 2, that would be 2p3. My 2p4 and 2p5. You don't know where it's going to go. So it takes the same amount of energy to fill either one. I'm just going to do it from left to right so that you have your paper should kind of match. This one could be going the opposite way, right? If I started with 3 down. Okay. Let's go to number 14. Ooh, 14. Now let's do 11. 11 was my iron. And number 11 on the previous page, it ends in 4s2, 3d6 for iron. So I could rock and roll through this. 1s2, 2s2, 2p6. You can fill them one at a time. Here's my p's. There's my 1s2, 2s2, 2p6, 3s2, then 3p6. It's hard to tell where you are, where you left off. That's why I just did some highlighting. After 3p6, 4s2, and I end with 3d6. 3d6. Here's my 5d orbitals. So I'm going to put 6 in there, but I need to start with all 5 up or all 5 down to start with. So again, it ends in d6 according to Hund's rule. It's more stable to have one electron in each orbital of the same spin before pairing. So there's my 3d5. You don't know where the 6th one's going to go, but you know it's going to be spinning opposite. I'm just going to put it in the first one. And then I know that these 4 right here have to be the same. Okay, Hund's rule, 1 electron in each orbital of the same spin before they pair up. It doesn't matter if it's P, D, or F. P, D, or F, it would not matter. I think for the last one, I don't have enough. I don't have them all on here. 5p6. If we did number 14, it's 4d10. 5p3. It ends in number 14. So I'm going to put them in. You can rock and roll through these. We're going to go to 4d10, 5p3. Three D10, 4s2, 3d10, 4p6. Then 5s2, 4d10, and then 5p3 way over here. We would have 5p3. We know those have to be the same. That's my 5p column. It ends in 5p3. So now you'll see some arrow notation. What is each arrow? It's an electron. All right, let's turn the page to 18. We good with this through 5p3? You get the idea. All right, on the next page. We are now going to do quantum numbers. And I'm going to go right down here to outline that. And I can explain quantum numbers here in about 14 minutes. I think we'll be pretty good with quantum numbers. So quantum numbers are a set of numbers, and it is n. Please just write it down like this in this same spot right here. NL. This is M sub L, little l, and then M sub little s like this. There are 4 numbers in parentheses separated by commas. And these 4 numbers are going to tell you where the electron is, what level it's in, first of all. So my first number is what energy level it is in. And that would be 1 through 7. My next number tells me the sublevel. Now, by sublevel, this is locked in. You use a 0 for an S, a 1 for a P, 2 for a D, and 3 for an F. So that's just a fixed number. This third number really tells you the orientation in space. So there's 3 different dumbbell shaped P's, right? One of them is along the X, one of them is along the Y axis, one along the Z axis. It's just the orientation in space. So that third number tells you the orientation in space, but it really tells you the exact orbital. These numbers go from minus L to plus L. Now, what the heck does that mean? That means we have to look at the previous number. So, if we have a P, if this is my P, my previous number is a 1, correct? That's just locked in. If I'm in a P, my second number is going to be a 1, locked in. To tell which exact orbital it's in, it goes from -1 to +1. We just number it like that. How many d orbitals are there? How many d orbitals? 5, correct? So if I have a d, I would have 5 orbitals. 1, 2, 3, 4, 5. And if I have a D, what's my previous number? A 2, correct? A 2. So if I go -2, -1, 0, 1, 2, that gets me all 5. That's what we mean now by minus L to plus L. And if we had an F, -3 to +3, that would be 7 orbitals, correct? -3 to +3. So if we had F, 1, 2, 3, 4, 5, 6, 7. So it would be -3, -2, -1, 0, 1, 2, 3. And the last quantum number is spin. And for the spin quantum number, if it's an up arrow going counterclockwise, it's +1/2. And if it's a down arrow, -1/2. Nope, I got those spins going the wrong way. That's 1/2 or -1/2. Okay. Let's do that right here. I'm just going to slide this over. I guess I better straighten this out. This is going this way. I got my arrows wonky. Now, we'll do this electron right here first. This electron right there, we're going to have 4 numbers. Let's go left parenthesis. My first number is the level. What level is it in? Level 1, correct? It's right there, level 1. My first number is a 1. My second number is locked in. 0 for an S, 1 for P, 2 for D, 3 for F. 0 for S, 1 for P, 2 for D. Right? 0 for an S. 0. My third number. -0 to +0. So my third number is just a 0, correct? And this is spinning +1/2. Four numbers tell you what level it's in. Which is the first one. It tells you what sublevel it's in. 0 for S, 1 for P, 2 for D, 3 for F. Then the third number tells you the exact orbital. And the fourth number tells you the spin. So if we do this one, left parenthesis, what level we in? We're in level 1, yes. 0 for S, 1 for P, 2 for D, so 0 for S. -0 to +0 or 0. And the last number, it's spinning the opposite way. Two electrons in the same orbital are going to have 3 numbers the same. The only thing different is their spin, correct? 2 electrons in the same orbital are going to have the first 3 quantum numbers the same. The only difference is the spin. Now, let's do this electron. So this is for carbon, right? This is carbon. This is carbon's 1s2, 2s2, 2p2. 1s2, 2s2, 2p2 for carbon 6 electrons. All right, let's do this electron right here. Left parenthesis. What level it's in? First one's my level. What level? 2, right? That's right there, 2. The next one is locked in. 0 for S, 1 for P, 2 for D, 3 for F. 1 for P, yes? My third number tells me the exact orbital once I go up there and number these. If this is a 1, this one's -1, this one's 0, and that one's +1. Which one is it in? Oh, it's in -1, right? And which way is it spinning? 1/2. This electron right here. Level 2. Next one is a 1 because it's in a P, correct? This second number is locked in. 0 if it's in an S, 1 if it's in a P. It's in a P, so my second number is a P. My exact orbital is 0. And my spin, 1/2. Three out of the 4 numbers are the same, right? 3 out of the 4 numbers are the same. Okay. Let's go down here. Well, we'll do this one first. What's my numbers here for this one going to be? 5, 0, 0, 1/2. It's in level 5. Second number's fixed. 0 for an S, 1 for P. Well, 0 for an S. Third number, -0 to +0, still 0. And then 1/2. This electron right here. This is 4d5, right? This is 4d5 according to Hund's rule. According to Hund's rule, d5. What I have here, I'm in level 4, yes? The next number, 0 for S, 1 for P, 2 for D, 3 for F. Two for D, yes, it's locked in. 0 for S, 1 for P, 2 for D. Got it right here, right? The second number is locked in. 0 for an S, 1 for P, 2 for D. So it's a 2 for a D. Now what? -2 to +2, correct? If this is D, -2, -1, 0, 1, 2. Well, it's in -2 for the exact orbital, correct? And the spin 1/2. Next one right here is 4, 2 again, right? Level 4, 2 for a D. This one's in -1. And the spin is 1/2, right? My third number is the only one that's going to change, correct? They're all in level 4. All 5 are in level 4. They are all in the D. 4, 2, 0, 1F. This one here, we're going to have 4, 2, 1, 1/2, right? And the last one is going to be 4, 2, 2, 1. Quantum numbers sounds complicated. How do we do? All right. So again, first number tells you the level, 1 through 7. Second number is locked in, 0 for an S, 1 for P, 2 for D, 3 for F. The third number tells you the exact orbitals. So once you know the second number, you just got to number them from the negative to the positive, except for S, you can just skip, right? So that would tell you the exact orbital, and then we have the spins. Okay. So there's Hund's rule, and then there's the Pauli exclusion principle, which basically says 2 electrons in the same orbital cannot have the same set of 4 quantum numbers, because they got to be spinning the opposite way. Okay, so we've done quantum numbers. Let's go back and we still have to do valence electrons. So I think that's where we're at. Yes. So for valence electrons, I wish I would have had you write all these out. So valence electrons are just the highest level S and P electrons. Highest level, furthest out S and P electrons. Those inter ones are called the core electrons. Highest level, furthest out. Highest level is the furthest out away from the nucleus then. So all we care about is the farthest out S and P electrons. Well, hydrogen here only has 1 electron. For carbon, the 1s2 we don't care about. Highest level, furthest out. We get to number 2, that's the highest number. We get 2 there and 2 there, so we get 4 valence electrons. Number 3. We don't care about the 1s2 again, but we've got 2 and 5. We've got 7 valence electrons here. Sodium. Once we hit level 3, we don't care about anything less than that. This just has 1 valence electron. This 3s1, just this 3s1. And for magnesium, we just got 2 there. Level 3, these 2, we get 2 valence electrons. Now, once we get to aluminum, how many valence electrons? Three. Sulfur has, all we care about is the highest number. Cover these up. We got 6, yes? 6. And for chlorine, seven. We go down to number 11. Some textbooks will say, oh, you include unfilled D's and F's. I'm going to stay away from that one. Just these two. 4F. We got to be highest numbered, furthest out S and P's. Well, there is no 4 P's, so we just have 2 here. Well, let's look at this. We can look at our blank table, or we can just look at our table here. How many valence electrons for neon? One S2, 2S2, 2P6. 1S2, 2S2, 2P6 is 10 electrons, correct? The 1S2 we don't care about. 2S2, 2P6 is 8, correct? We go to argon. 1S2, 2S2, 2P6. 3S2, 3P6. 8, 3S2, 3P6. Krypton. 4S2, 4P6. 8. Xenon. 5S2, 5P6. 8. And radon. 6S2, 6P6. 8. All of our noble gases here, except for helium, 8 valence electrons. Now let's back up to this, to the group 17. This element right here, 2S2. Just think of your columns on your blank table. 2P1, 2P2, 2P3, 2P4, 2P5. How many valence electrons? 7. The 2 from over here, here's your 2S2. And then the P1, P2, P3, P4, P5. 7. How many valence electrons here? 6, 5, 4, 3, 2, 1. Everything in group 1, 1 valence electron. Everything in group 2, 2 valence electrons. Everything in group 13, 3 valence electrons. It's the ones place. 3 valence electrons, 4 valence electrons, 5 valence electrons, 6, 7, and 8 for valence electrons. All we have to do, this is very important for the next chapter, all we have to do is look at the ones place of the group number. So, selenium. Is right here. How many valence electrons? 6, right? It's the ones place. Selenium should have 6. Krypton. How many valence electrons for krypton? 8, right? Noble gas, what group is it in for krypton? It's right here. It is in group 18. SB antimony is right here. What group is it in? 15. 5 valence electrons. Noble gas xenon is going to have 8. And we can do the last one. We can see what it is. It's going to be. Bismuth is right here. It is in group 15. We know it's going to be 5. Where are they? They're right here. Those are the 5 valence electrons. The farthest out S and P electrons. Right there, or if it's written like this, right here. So again, valence electrons should match the group number. Group 1, 1 valence electron. Group 2, 2. Group 13, 3, 14, 4, and so on. Now, let's add that to our blank periodic table here on page 20. Group 1 and group 2, valence electrons. Valence electrons. Then it's going to match the ones place, right? The ones place. Except for helium has 2, right? Again, it's just the ones place. We're going to use that all the time, the next chapter. Now, I can explain these 2 exceptions to the octet rule, or to our electron configuration notation. So if we look at chromium here, now your electron configuration notation's on your table, right? Notice we predicted that it would be 4s2 3d4. That's what we wrote down. 4s2 3d4. But it's really 4s1 3d5. One of the electrons goes out of the S, goes into the D. What's that create? 1 electron in each orbital of the same spin. D5, yes? That is really stable. They like that. Notice now, molybdenum does the same thing. 5s1, 4d5, right? One of them goes out of the S and goes into the D to give you a half-filled D5. All 5 up or all 5 down. Then once you know it, you can never trust an electron. When you think you have it figured out, then tungsten doesn't do it. Okay, so for this one, we know that this is S1D5. And what that does is it gives you this D5. 5 up or 5 down. It likes that. What's the key to why it does any of this stuff? It is more stable. There's a lot going on. You've got all those negative electrons that don't like each other, correct? So they're going to do whatever they can to minimize the repulsion from neighboring electrons. It's more stable, D5. A P3, D5, half filled, F would be F7. $29. What is the real configuration for copper, silver, and gold? Copper, silver, and gold. If you look on your periodic table, it is not S2D9. It's S1D10. What's the most stable configuration? Fill that sucker up. Fill that up. So these are all right here. S1D10. It fills up the 10. What's the key words? More stable. So some of this you can explain, makes sense, makes it more stable to take one out of the S, fill up that D. But again, like I say, once you think you've got it figured out, so all of these do it, and then here tungsten doesn't do it. Okay, let's backtrack now. We're getting close to being done with 7. Let's see what we've got next here. Oh, and by the way, I'm going to backtrack farther. You don't have to backtrack this far. I'll just put it on the screen. I simplified these quantum numbers from page 13. So on page 13, because I was going to ask you for these goofy names. Remember, we had N, L, M sub L, M sub S, correct? And I called it the level. Well, N is really called the principal quantum number. It really tells you what level. L is named the orbital angular momentum quantum number. It really is the subshell, SP, D, or F. M sub L is named the magnetic quantum number. And orientation in space, I say it really tells you the exact orbital, and then it still a spin. So you're going to see, I'll kind of ask you for a drop down, I think, for these. Okay, so now I think we're in order, and we are on page 19. And we're going to add this to our periodic table. So we did quantum numbers. Now, elements in groups or vertical columns of the periodic table exhibit similar chemical properties or similar chemical behavior because the elements in the same group have the same number of electrons in their valence shell. They have the same valence electrons, correct? Everything in group 1, 1 valence electron, correct? So they act similar. Everything in group 2, 2 valence electrons. They're going to act similar. They have the same number of electrons. Things react according to the electrons. Now, going down a group, atomic size increases. So just going down a group, it should make sense. There's nothing to think about on this one. As you go down the group, This is energy level 1. While energy level 2 here gets bigger. Energy level 3 gets bigger. Energy level 4 gets bigger. 5 gets bigger. 6 gets bigger. 7, right? Going down a group. It just gets bigger and bigger and bigger. You're adding electrons. You're adding more levels to get farther away from the nucleus to pack them in. So going down a group, atomic radius increases. Going across a row or a period across, the size generally decreases. You're adding more protons to the nucleus, but you're not adding more levels. So let's add that to our periodic table, our blank table. So I'm going to draw an arrow going down like this, and we're going to summarize it. So I'm just going to draw an arrow going down. And going down, the first thing we just did, and that's atomic radius increases, right? Atomic radius is going to increase going down. And I'm going to make the arrows go the same direction. And now I'm going to go across. And I'm going to draw an arrow from left to right. And here, atomic radius generally decreases. Of course, it can't be 100% because you can't trust an electron. So just atomic radius makes sense. Now let's go with the next. So I got to back up. So we good with atomic radius increasing down, generally decreases as you go across. Now, this concept. The energy needed to remove the most loosely bound electron. What is that called? That's called ionization energy. Now, let me ask you a question. On this table, which elements do not want their valence electrons? Which elements do not want their valence electrons? Those are the ones that get rid of their valence electrons to form a positive ion. Sodium does not want its one valence electron. The goal is to be like the normal gases over here. These are the king cool elements. Neon, argon, krypton, xenon, radon. How many valence electrons do they have? 8. That's the goal. What is the most stable configuration? 8 valence electrons. In fact, these noble gases are so stable, they do not form any compounds. There's no such thing as neon chloride, argon nitrate, argon phosphate, krypton chloride, anything like that. They don't. How do you make a compound? It's the interaction of electrons, correct? It is the interaction of electrons. The most stable configuration, 8 valence electrons. Sodium, if it gets rid of 1 electron, how many valence electrons will it have? It'll go from 11 down to 10. just like neon. Potassium. How many valence electrons does potassium have? One, but it didn't want the damn thing. Because if it gets rid of the one electron, instead of this 4s1, it's going to be 3s2, 3p6, the same as argon. Elements over here, metals over here, do not want that electron. So if ionization energy is the amount of energy needed to take an electron away, think about it as pull, pound. You're in a tug of war. It's not going to take much to tug away an electron over here. But let's get more specific. Is it going to be easier to pull an electron away from sodium or an electron away from cesium? And why? Which one's going to be easier to pull an electron away? What's pulling the electrons in? The nucleus, correct? The positive protons in the nucleus are attracting those electrons. Would it make sense if this electron in cesium is clear out here in level 6, that it would be easier to pull cesium's electron away than sodium sitting here in level 3? Level 6 is a lot farther from the positive pole of the nucleus, correct? So as we go down a group, ionization energy, it's going to get easier to pull that electron away as you go down. Remember, you're just trying to pull that one valence electron away. The farther it is from the positive pole of the nucleus, the easier it should be. So as we go down, number 2, ionization energy. Which means you're going to take away an electron. Going down, it's going to be easier. So it decreases. That's why all of those elements on the left form a positive ion. How do you form a positive ion? You get rid of an electron, right? What about if we go across the table? These elements over here want their electrons. In fact, they want to gain one more. If fluorine gains one more, boom, 10, just like neon, yes? Chlorine gains one more. These are all P5, correct? S2P5, 7 valence electrons. It wants one more electron. It's going to be pissed if you try to take one. They're going to put up a fight. Sodium's not going to fight. Here, have it. Right? These over here are not going to put up a fight if you want to take an electron. These over here are. Because they want, these non-metals over here want to gain electrons. So as you come across, they want their electrons. It's going to take more energy to pull an electron away coming across. So as you come across from left to right, ionization energy increases. Probably there's an exception. I should probably have generally in here. I'm sure there is. So what's ionization energy? Energy to pull away an electron. Now, the last one on here is electron affinity. Oh, boy. So what is electron affinity? Adding an electron. So you want to add an electron. Which ones want the electron? Which ones want you to add an electron to them? These nonmetals, correct? These nonmetals over here want an electron. It's not going to take much energy for you to give them an electron over here. These don't want their valence electron already. You try to give them another electron, they're not going to be too happy. It's not going to go so well. So electron affinity, add in an electron. Electron affinity. Number 3, electron affinity. Add an electron. And I'm going to check going across to make sure. Electron affinity increases going down. And here, electron affinity decreases. It wants an electron anyway. Generally, yeah, generally, yeah, decreases. Okay, let's go back and answer then our question right here. Using only a periodic table, arrange the following elements in order of increasing atomic radius. All of these elements, krypton, xenon, helium, neon, are in group what? This is group 18, correct? Group 18. Helium, neon, xenon, or excuse me, krypton, xenon. Which one has the greatest radius? Xenon at the bottom, correct? So I think what Al does, it gives you boxes and it goes like this. I'm pretty sure it goes like this. Helium's radius is less than neon's. Neon's is less than krypton's. And krypton's is less than xenon. I think that's the way it answers it. Next one is ionization energy. Looks like it's group 1. Hydrogen, sodium, potassium, cesium. Now, ionization energy to pull an electron. Which way does this go? Which one's going to be the lowest ionization energy? The easiest to pull an electron away? Cesium. That electron is way, way out there. So it's going to go like this. Cesium is going to be the easiest. The last question on here is going to take a little bit more. So we are going to be done with chapter 7 next time we meet. Print off the next unit if you've not for this quiz. You can do all of these, but number 33. You can do all but number 33. So work on the quiz. Print out the last unit. I believe there's a learning guide is 8 and 9. That's it. So bring the last one, print it, however you want to do it.